Let's do some calculus in polar coordinates. We're going to look at an example of the graph of r equals 1 minus sine theta. That's a super famous kind of graph that works well in polar. It's a cardioid. I've sketched it here. Of course, I can always talk about x and y coordinates. We're actually going to do a lot of stuff in this video that sort of refers to, even though it's a polar graph, refers to things like horizontal and vertical and slope that's more naturally in x and y. And if you graph it out, you get r equals 1 when sine theta equals 0, when theta equals 0, so sine theta equals 0. As it comes around, the radius goes to 0 right when theta is pi over 2. And then it rebounds and goes to back to 1 when theta is pi, then goes all the way up to 2. So this is r equals 2 because I'm pointing in the 3 pi over 2 direction, and then comes back. So this one in particular has no negative r values, so it's going to be a little simpler for the analysis. But you can do this with negative r's, but it's substantially trickier, especially for area. So here's the three questions I'm going to address. Where is the tangent line horizontal or vertical? Another tangent line question, let's pick a point and figure out the slope. And then a rather different question, what is the area inside this? Okay, so let's look at the tangent line. So this is something that, say, Stewart addresses. We want to get dy dx, and this doesn't mention y or x explicitly at all. And a good way to think about it is we can figure out y and x by calculating, by looking at the conversion formulas. Y equals r cosine theta, and sorry, y. I don't know why I said y first. Let's do x first. X equals r cosine theta. Y equals r sine theta. And so given this information, if I tell you theta, I can get r because that's the curve, and then I can get x and y. And so what I've got is a situation where I can think of theta as the parameter for a parametrized curve. Now I want to make sure I say there's a lot more to polar coordinates than just a certain kind of parameterized curve. You really want to think of r and theta geometrically in their roles as measuring angles and measuring distances away from the origin. But one trick you can use sometimes, and here's a good place to do it, is just to think of it as a certain parametrized curve. So in particular, x here is going to be 1 minus sine theta times cosine theta, and y is 1 minus sine theta times sine theta. So if you just do that and just do parameterized, then you're going to be good for this particular kind of question, anything about tangent lines, as long as you're good with the parameterized story. Now, if you want the general formula, you can always look at this and take the derivative with respect to t. Remember, this was dy dt over dx dt. But now it's going to be theta is the parameter. And you can do this with a little chain rule, a product rule. And so you're going to get, ooh, do I have enough room? I think I do. Dr d theta times cosine times sine theta, sorry. This is going to be y here. Plus r cosine theta. It's really just a product rule. I guess I really shouldn't have said chain rule. Divided by derivative of this guy, dr d theta, cosine theta left alone, minus r sine theta. I know that's kind of squished in there. Okay. All right, so you can either just do this directly, plug in the formula for r, and just do this and not memorize this formula at all, or you could have this formula available. On EAP, it's probably better to not even try to memorize this. There's one more thing to memorize, and just think, hey, I know these formulas. That's something you absolutely need to know. Plug in your formula for r, and just treat this as a parameterized equation. But let's see what happens when we do it in this particular way. It's essentially equivalent. Okay. In this case, dr d theta is going to be minus cosine theta, and then times sine theta, plus, and then 1 minus sine theta, the whole quantity times cosine theta, all over, I erased that, dr d theta, again, is going to be that same minus cosine theta, minus the quantity 1 minus sine theta, sine theta. Better, simplify at least a little bit? Well, I've got a minus cosine theta sine theta and another minus cosine theta sine theta. That's minus 2 cosine theta sine theta. That might be nice to write as minus sine of 2 theta. Not always clear if you want to take advantage of a double angle like that, but let's try it. In particular, there's a bit of a mismatch here. We can always re-expand it. But I wanted to point out that it's nice to be on the lookout for those kinds of identities. Here I have minus cosine squared. Ooh, minus a minus sine squared. So remember, that's not going to be sine squared plus cosine squared. It's, let's just write it out, minus cosine squared theta plus sine squared theta. And then again, then minus sine theta. I seem to be getting some weird flashes. I don't know why that's going on. Okay, and this is, again, a double angle formula, but again with a minus. Okay, so this is kind of cute, but we have to watch out for the fact that we've got a mismatch between two thetas and thetas. We might have to just unpack it again, depending on what we're doing with it. Okay, so there's a relatively nice formula for the slope of the tangent line at any point. And then I can go back and ask questions about where is it horizontal, vertical, and look at various specific points and get the slope. So, as usual, if I want to know where this is horizontal, that's going to be where the vertical motion dies as long as there's some horizontal motion. Or in other words, where dy dx, of course, is equal to 0. So 0 on top and non-zero on the bottom. And so I would set the top to 0. So that's where we see that this double angle isn't the absolute best thing, because we're just going to have to solve an equation, and I'll show you how we're going to have to unpack it again. So I love double angle formulas, but it's important to not be too wedded to them. We want the numerator equal to 0, and that's going to be minus sine 2 theta plus cos theta equals 0. I think I'm going to have to re-expand this again. But when you do, it's not too bad. So I get a product, cosine theta times the quantity 1 minus 2 sine theta, all equals 0. Okay, so either cosine theta equals 0, or 2 sine theta equals 1. Now, when cosine theta equals 0, there's two possibilities. Theta could be pi over 2, but we've already seen there's a cusp there. That's not a horizontal tangent line. That's just a fairly bad point that's going on there. Let's see what happens with the denominator. When theta equals pi over 2, this is minus 1. So this is plus 1. Ooh, minus 1, you get 0. And when both numerator and denominator are 0, you need a much more subtle analysis to figure out what's going on. And we already know that it's got this nasty cusp. Okay, so that's really not a good example. Okay, now theta equals 3 pi over 2 is much nicer. We can see from the graph that that is definitely a place where the tangent line is horizontal. And if you check it, that's where this is still going to be minus 1. This is plus 1, but now this is plus another 1. And so it's not going to be 0 over 0. Okay, so that's a check. And then here, so this was pretty obvious that we saw that really from the symmetry of the graph. You can see that. And then here, sine theta equals 1/2. Theta equals either pi over 6 or 5 pi over 6. Not surprisingly, we're getting two angles that are diametrically reflected across the y-axis. These are supplementary angles, and that's how you detect reflection across the y-axis in polar, and those are the places at the sort of the top of the heart. In the next one, we'll continue this and find some more slopes and then move to the idea of finding area.